All right, we're going to look at applying sequences. So we're going to take our idea of arithmetic and geometric sequences and apply them to a contextual situation. All right, so we have our two sequences, arithmetic sequence and geometric sequence. So we're going to discuss when to use which. So when reading a situation, kind of identifying which one, what model it fits. So if we look at arithmetic sequence, reminder is a situation that has a constant change of addition or subtraction. So if we're reading a context, we're either adding something or subtracting that same thing over and over. That's going to be our linear growth. And it's linear growth because of that idea of its constant change. So when we find that as we're reading a problem, we're going to identify as our linear growth. And to remind ourselves, that means we're fitting in our explicit for arithmetic, which was the common difference times the term number plus our term zero or our initial. Geometric sequence is a situation that increases, I should say, through multiplication or division. It's exponential growth or decay. So it's either growing by multiplying by the same value over and over, or it's decaying by dividing by the same number over and over. So that's where that exponential comes from, through that multiplication process. We can also identify it by having a percent increase or a percent decrease. To find a percent increase, we take 1 plus the percentage. That's going to give us our multiplier. We'll discuss that when we get to a problem like that. Or a decrease, we would subtract from 1 the percentage. Some other keywords, doubling, tripling, and halving, are some kind of key indicators that we have an exponential problem or a geometric sequence that applies. Our explicit for geometric is going to be term 0 times our multiplier b, or our common ratio, we called that, to the power of n. When we're talking about word situations or contextual problems, explicit equations are the way we're going to go. The recursive equation, I get a question a lot of times, when would you use that? The recursive equation is another way just to describe a sequence. The explicit is more useful. It is more direct. It helps us identify pieces with more ease. But it is there. Recursive is there. But we're going to focus on the explicit equations for application. So let's go ahead and look at example 1. The first row of dominoes of a dominoes display has 10 dominoes. Each row after the first has 2 more dominoes than the row before it. How many dominoes are in row 100, and what row has 64 dominoes? In this problem, we're adding 2 dominoes every row. So right there, that tells us it is arithmetic because it is linear. Linear growth of adding 2. So we're going to go ahead and we are going to start with our difference. So our difference is positive 2. And our term 0, now I have to think, if the first row has 10, if we could go back a row to the 0th row, we would call it, it would have 8. So our term 0 is 8. Giving us our explicit equation, T of n equals 2n plus 8. We're going to use this to answer our first question. How many dominoes are in row 100? So what we're looking for is, what is T of 100? So we're going to plug in 100 for n in our explicit, telling us that row 100 has 208 dominoes. The second question, what row has 64 dominoes? Well, the number of dominoes is the term value in the sequence. So we're not going to plug in 64 because we're not looking for the 64th row. We're looking for 64 dominoes. So 64 is going to go in our T of n spot. So 64 equals 2n plus 8. And when we solve that, we're going to get an n value of 28. So remember, this is the row that has 64 dominoes. This is the amount of dominoes in the 100th row. Example 2. A movie earns $100 million the first week it is released. The movie earns $20 million less each additional week. Write an equation for the nth week after it was released. Again, if we look, we are earning 20 million less each week. So right there, arithmetic. So this is arithmetic because it has that linear change. Our common difference is negative 20 million. And our term 0 is 120 million. Remember, 100 million would be the first week, so we got to go back to the 0th week, which would be 120 million. That gives us an equation of negative 20 million. Forgot my n plus 120 million. Example 3. A new cell phone, the Pi phone, is set to be released January 1st. The store anticipates to sell 1,000 pre-orders. Pre-orders meaning before sales, so week 0. And forecasts sales to increase 15% each week. How many phones will they need at the end of the quarter? All right, so here we have an identifier of geometric because it's increasing by a percentage. Because it's a percentage, we're multiplying by a multiplier because the percentage will change based on the week before. It's very similar to our rabbit problem we discussed earlier in our unit. All right, so this is geometric because it has percent change. That's kind of our identifier, percent change. Now, this is an increase. So to find an increase, we take 1 plus 15% as a decimal, which is 0.15. This is just like last year when we worked with markups, or very similar to markups. This gives us a multiplier of 1.15. So this is our B. So it's a 15% increase. Our term 0 is 1,000 because of it telling us about the pre-orders. So our equation, T of n equals 1,000, our term 0, times our multiplier to the power of n. Now, we want to find out how many phones we'll need at the end of the quarter. So a quarter is a fourth of a year. A year has 52 weeks, so a quarter is going to be 13 weeks. So we're finding T of 13. So 1,000 times 1.15 to the power of 13. This gives us a value of 6,152.78 phones. So if we want to have enough, we would need 6,153 phones. We're going to round that up so that we have enough phones. B, a rival phone, the Pyroid, is also set to be released. They have 10,000 pre-orders. but are forecasted to increase only 7%. Write an equation for the number of pyroid phones they will need for the nth week of the year. So it's the nth week, so we're going to keep n in our equation. All right, so T of 0, our pre-orders here, similar to our last problem, is a little higher. It's 10,000, so they're selling more initial. Now our multiplier is 7% increase. So we're going to do 1 plus 0.07. So the multiplier is 1.07. That represents a 7% increase to the nth power. And our last problem. Oh no, the pyroid forecast was incorrect. They sold more initial phones, but sales decreased 3% per week. Write an explicit and a recursive equation for pyroid sales. All right, so our initial is still the same. It's 10,000. But now our multiplier, we're doing a 3% decrease. So we're going to take 1 and we're going to subtract 3% as a decimal, giving us 0.97. Explicit, T of n equals 10,000 times 0.97 to the power of n. So that's our explicit for the nth week. And our recursive always starts T of n plus 1 equals T of n. So the next term is equal to the previous term times our multiplier. We're multiplying each week by 0.97 to get our next week. And we're just going to state what the 0th term is, 10,000. Typically, we would say term 1, but usually we have term 1. Since we don't have term 1, we have term 0, we would go ahead and we can list term 0. As long as we give some term in the sequence for the recursive, we are good. All right, so the last thing I want to do, if you feel good about it, you're good. I am going to review just our multipliers with percentages. So if we look at just a quick reminder, tends to trip some students up. Just it's an easy one to make a mistake. So if we have percent change, so these are our percent changes, we're going to show how to calculate them and what the common ratio would be. So if we have a 40% decrease, that means we're going to take 1 and we're going to subtract 0.4. 0.4 is 40% as a decimal. If we go ahead and do that, we're going to get a common ratio of 0.60 or 0.6. For a 15% increase, it's an increase, so we're adding. So 1 plus 0.15, giving us a common ratio of 1.15. 200% increase, 1 plus, notice, we always start with the 1. We're adding 200% as a percentage is just 2. So our common ratio would be 3. That one tends to trip students up. They say 200%, they think our ratio should be 2, but we have to add that to 1, giving us a ratio of 3. And then our last one, 75% decrease. 1 minus 0.75, leaving us with a common ratio of 0.25. So if we have a decrease, our ratio should be below 1. And if we have an increase, our ratio should be above 1. This is an intermediate step. This is just showing us how we go from here to here. If you can go from this to this right away, by all means, go for it. And I hope this helps with applying our sequences to an application problem.